Welcome to everybody to this very special edition of the Strong 2020 public lecture series. Up to now, all our public lectures, and this is probably the 13th one or 12th whatsoever, have been lectures which presented you some issue in the framework of our Strong 2020 European project. This one, it's very special, and somehow it's for us kind of a new type of lecture because it's a virtual visit to the vMAMI facility in Germany. I am Caterina Corciano, and I am leading the work package dedicated to communication and dissemination within the Strong 2020 European project. And before leaving the floor to our host in Mainz, I wanted to tell you something, some words about our Strong 2020 project, which it's a project which started in June 2019, and it's a big community involving more than 2,000 researchers dedicated to the study of the strong interaction at the frontier of knowledge. And the project itself is performing fundamental research and also applications related with the strong interaction research. And the project brings together many groups and infrastructures in Europe and exploits, as you can see here, innovation potential in applied research, which comes from the development done within our project. And as I told you, it's really a big project. It involves 45 participating institutions from 14 European member states, one international organization, which is CERN, and one European candidate country, and has a lot of projects inside. So there are a lot of activities. Actually, project is structured in 32 work packages, which involves also 7 transnational access activities, which means activities at main infrastructure in Europe, among which we have also vMAMI, the lab where we are visiting today, which I'm very happy we can do this, but also some research activity within joint research projects, virtual access activities, and again, some network activities related with strong interaction studies. As I was already mentioning you, today we have a very, very special lecture, which is actually a virtual guided tour to the vMAMI facility in Mainz in Germany, and our hosts there, Pepe Gülker and Stefan Aulenbacher, are eager to bring us in the research infrastructure, which is part of the transnational access within Strong 2020. With this, I stop sharing, and I invite the two hosts on the floor. But before doing this, let me tell you that in order to better see the visit, they advised us, as you see, to click on the 3 dots in their names. So where is the part written Stefan Aulenbacher? Click on the 3 dots and then on pin option. Then you will see better the hosts and the virtual visit in vMAMI. So please, our host, Stefan, I leave the floor to you, actually the screen. Are you there?
Yes, we're here.
Yes, hello.
And we directly start with a tour, with a little introduction video.
And not to forget this, thanks for the introduction,
Yeah.
and thanks for having us here. And as you already mentioned, we're eager to give you a tour through our accelerator. So enjoy the intro.
Sehr geehrte Damen und Herren, herzlich willkommen zur virtuellen Führung der Beschleunigeranlage vMAMI. begleiten Sie uns auf eine Reise durch die Welt der Teilchenphysik. Und hier sind Ihre Gastgeber, Pepe Gülker und Stefan Auen.
Hello, hello. Sorry for the introduction to be in German, but actually we did this during the Corona pandemic. I think you have to switch our whatever.
okay.
We started this during the Corona pandemic to have a virtual tour, and now we more or less found out that it's still a great idea to have people from further away to show through our facilities.
Yeah, and we here currently what you see is the actual lecture hall of the Institute for Nuclear Physics in Mainz. And before we start, is everyone hearing us?
Yeah,
Is this
great
all working?
We do hear you.
So-
We do hear you.
Perfect.
great.
Yeah.
I mean, this is what it was written and in the introduction already told. This is a virtual or interactive tour, so you're always able to ask us questions like in real life.
Please interrupt us.
Yeah, just interrupt us.
Necessary. Yeah.
I mean, this is not a video. We are sitting here live in the office and doing this for you. So please ask questions because there's so much stuff to tell, and it's better to kind of to know our audience. And for this, I would like to start, perhaps use the chat. And if you could just type in a P if you're a physicist or an N if you're a non-physicist, that we know how to address you. This would be nice. I don't see anything yet. So please put in the chat a P for physicist. And oh, we have one physicist.
Oh, we have a lot of physicists.
Okay, great. Good to know.
I guess we have only physicists.
Yeah, so we will be brief on the introductory.
Yeah, so usually we do this tour for non-physicists. So therefore, there are a lot of things we explain which you might already know. Yeah. Hopefully it's not so boring for you.
Come on,
the introduction. Let's just start. So usually we used to ask people what is a particle accelerator and how do you picture a particle accelerator, because most of the people have a clear picture in their head.
Yeah, it's a big ring.
It's a big ring, it's a big circle, and a beam pipe with a diameter like that. So something in the order of half a meter or something. And yeah, this is usually the first thing where we start and say, yeah, okay, there are different types of particle accelerators in this world. And of course, you know that not everyone is a ring. I mean, obviously, the reason why people thinking about a ring is the LHC in Switzerland, because this is the most famous accelerator in the world. And
sure, the biggest one.
Yeah, but therefore there are linear accelerators, and there are a lot of accelerators with a combination of a ring and a very weird structure like we have in GSI. But in our case, we have a fixed target accelerator, and which is not just a straight line. So vMAMI is a linear accelerator with a technique called racetrack microtone. And we will explain later how this is working. But in total, we have a length of 7 kilometers and it's built up very compact.
Yeah, it's very compact. And as you can see here already, we have different, I mean, sure you see it, we have different accelerator stages. And they all more or less have the same principle. Actually, on this on the sketch here, the last accelerator stage isn't even shown.
Yes.
I'm just seeing this right now. So we have 4 stages, and we will go through all of them and show you the working principle of the microtron. And actually, the acronym MAMI stands for Mainzer microtron.
Yes. So then the next thing one should talk in an introduction about is, for what is a particle accelerator? And you know, this question is not easy to answer at all because there are a lot of approaches. However, one should a little bit talk about that topic because, you know, a particle accelerator is just accelerating particles, not more. One needs to do something with that particles. And therefore, we usually explain that one can compare a particle accelerator with a microscope. However, I think we can do this quickly.
We can do this, I guess, very quickly.
Yeah, I guess very quickly, since you are physicists. Yeah. Is there some non-physicists? No, there's not.
No, actually, I think we have.
Yeah.
Or they were quite the non-physicists.
Yeah.
I guess we have none of them.
Okay. So
I mean, as you know, visible light is somewhere in the nanometer range, in the bigger nanometer range. So it stops. We printed here, or we put here this virus. I mean, some viruses you're able to see with visible light, but below this you're just not able to resolve the structures. And this is why we need something with more energy. To resolve what we put here in the picometer scale, to resolve atoms, or even to go further in. I mean, we're here for STRONG-2020, so we want to see the nucleus and the parts of the nucleus.
yeah, and of course, MAMI, one of the biggest topics in MAMI is to clarify subatomic structures. To make experiments on structures of nuclei and also on hadrons. And
this is why we just need the energy to resolve structures in the femtometers.
Usually we talk about then the Broglie wavelength and things like that.
But this we can.
I guess we can skip this, and hopefully we don't have to explain this one. I think you're all familiar with the definition of an electron volt.
Yeah, I mean, just to keep this short, this is a unit for energy.
Yeah.
And I mean, we're not going to use joule here because it's just too big. So we are going to use electron volt. And this, the energy, 1 electron, as the name suggests, gains when it's accelerated by 1 volt, as we sketched it here in a condensator.
So, but since you want to see the machine, we should go ahead to see the machine. And people told you we started to doing that virtual tour during the Corona pandemic, where we were not able to make actual tours. And therefore, our idea was to make it feel like an actual tour. And this is why we're not now bringing ourselves directly into the hall. We are walking there right now. You see the actual way through the institute.
Yeah, I mean, now here we have all the one how it's called, one gang with the
floor.
We have one floor with the offices. In Mainz, there are roughly 200 people working at the institute. Like more or less half of them scientists and the other half non-scientists.
Yeah, and you see, we did this in the middle of the summer some years ago. Here are things to say, because you see there's a lot of stuff stored outside. And here where you see that blue crane in here, today there's a building, and this is the building for our new accelerator we're currently building up, which is called MESA. And
so hopefully we're able to welcome you in a few years to show you through the new accelerator.
And here, where I brought my picture right now, it's exactly in here. This is where we're sitting right now. Here's our office where we're sitting to give you that tour, just that you know that. So now we are entering in a couple of seconds the hall where the accelerator actually is. I think
now actually we're going above. We're walking above the accelerator. We'll show you a map of the whole facility in a few minutes.
In a few seconds.
In a few seconds, actually.
Yeah.
Great.
Yeah. Okay. So here we are entering the hall where the actual control room of vMAMI is. You will see in a couple of seconds. Yeah. And in the meantime, I think we should tell you a little bit about ourselves. So Pepe and me, we are both PhD students in the so-called MAGIX group. This is an experiment at the new accelerator, but it's kind of normal that everyone does tours, and especially me, since I have some outreach jobs to do, and therefore I made this guided tour, this virtual tour together with Pepe. So we filmed them a lot, and you will see some nice pictures and in a couple of seconds.
So actually now we already entered the control room of our accelerator. You see, it's not the newest technique, but it's working very stable. I mean, this in the particle accelerator world, this is what Mainz is famous for its great beam quality and for the stability of the machine. I mean, we're more or less running all through the year, and I think this is very nice doing experiments here, that it's just working very great.
So maybe we will tell you a little bit more details about the control room later. But now let's go to the elevator.
Yeah, may I stop you just for a moment to give you and to remind you that you have the opportunity to ask us questions all the time. So, I mean, perhaps now that you blank the screen, are there any questions for the introduction?
So far, yeah.
I mean, perhaps we're going to help in the elevator anyways, and be able to ask some questions there if you already have some.
So now we're bringing ourselves 8 meters down. Yeah. And so vMAMI in general is built 8 meters underneath the floor. Of course, you know the reason for that, to prevent radiation to come out and to prevent disturbing things to come in at the same time. And so here we are, and -8 meters. And what you see first here, the red block is the door, which is a giant LED block, which we bring in inside the wall when the machine is running. So here we have a floor plan, and we start our tour. Always keep an eye on Pepe here. Yeah, we are currently here, and you see this is the first stage of vMAMI we will see first. Then here we have the second stage, the third stage, and here are the experiments. We will see that all, and we will later.
Actually, sorry to correct you, the stage is always +1.
Yeah,
I think you have, I mean, you have the numbers here. So we have this 3 racetrack microtrons, and then this harmonic double-sided microtron, which
we will see
stage 4.
Everything of them.
Yeah, I think we'll skip racetrack 2, but they're all the same. Okay, so this is what we're going to have a look at, and then I think we're also going to visit one experimental hall. Like A1, we'll see how short we have to, how much time we spend. Perhaps we're also going to see A2. I mean, this is what we have. We have this accelerator. Most of you are familiar with this, but we're not running one experiment all the time. We have different experimental halls, and more or less the accelerator runs all the time, and then we guide the beam into different halls, that the other halls are accessible, and we're whatever improving the experiments, building up new stuff, and then having what we call a beam time for most of the time several weeks. So okay, finally let's see the machine.
So this is the very beginning of the machine. This is the source. Yeah. And unfortunately, this is one of the parts where one cannot see because it's completely inside of the box in here. But what happens in there, I guess this is clear to you. This is a glow cathode. This is one source. We have two different sources. We have a glow cathode and we have a laser-driven source.
Why you need two?
For the laser-driven source, we need to produce spin polarized electrons, which we don't need for every experiment. So the intensity of that beam is lower. So therefore, one only produces them if they are really needed for the experiment you want to do. And after that source, we preparate our beam. We have to I mean, this is a continuous source, yeah. And then, of course, we apply a Wien filter, we apply a collimator, and then we have a so-called buncher, which we use
chopper,
buncher and chopper, yeah, to bring the electrons in bunches. So our accelerator every accelerator is only working with a pulsed beam, which you see right now, because this pulse beam enables the option to accelerate them in such a structure called the cavity. Now in that cavity, you can think about, well, let's open it. This is an actual CAD drawing of this cavity. And we break this structure down in order to see what's going on. We can think about that this is like a capacitor, a row of capacitors. And of course, if we charge them, you see the electric field looks like this. You see with that arrows, and all arrows which are blue are an accelerating field, and all the red arrows are decelerating field. And of course, what one has to do is to have a oscillating field, so that electrons which are coming in right now always see an accelerating field, and therefore they have to be pulsed.
They have to be bunched.
They have to be bunched. Yeah, and so it's a matter of timing. However, talking about timing, we need our field to oscillate with a frequency of 2.4945 gigahertz. And there is not a power supply which can do that. So therefore, we're not charging the capacitors. There aren't actually any capacitors. There are those small holes you see in here, those small cavities. And what we do is we bring in microwaves, and they can resonate perfectly in that structure, and the field you have in the end is exactly the same field which you would have if you would apply alternating current.
I mean, if they're built the right way, this is what we have. I mean, these so-called cavities or resonators, they more or less just feature one mode. This is why they have to be built very carefully, that you really have this one resonating mode only. And just to here you see the machine a little bit. We have this 2.45 gigahertz. Yeah. I mean, we have it all the time, but here, I mean, this is the linear accelerating stage, what we see here in the beginning. Rewind it a little bit. I mean, here the electrons are really accelerating, so they're taking up speed in a classic way. And this is why all of these, and we'll see later the difference. Like here, you have special built cavities.
They look every individual cavity looks different.
Yeah. this symbol, they have to get bigger all the time because the electrons speed up. And more or less what you see here on the left, perhaps you're able to move over there, yeah, directly beneath Stefan. There, the electrons already hit essentially the speed of light.
Yeah. And you see in here, here's the first cavity, the second and the third. And this is what we call the pre-accelerator. At the end, paper just said it, at the end, we are at speed of light. One can say we are at speed of light, or at least one can say the velocity, the actual velocity of the electrons is not changing anymore. And this is what we do need, because this enables then the concept of RTM, which is called racetrack microtron, which is our idea of accelerating, which we see next. This is going around the corner at the end of the pre-accelerator. And in here you see a magnet. This is where I am here, the green thing, a magnet. But we will break it down a bit that you can see it better, that picture. So what's going on in here is actually, see, this is the drawing of that structure. We have two magnets and one cavity here in the middle. And as you can see, yeah, dipole magnet. And yeah, of course, this drawing here is made for non-physicists. Yeah. I guess you are very familiar with what's going on. We are going around the corner for 180 degrees with those electrons, and they are accelerated in that cavity. And with that technique, we can use one and the same cavity multiple times. So therefore, we save space, we save costs, and a lot of things. Yeah.
Yeah. So this is really the basic idea of a microtron, to reuse this cavity and to have like a fixed amount of energy that the particles gain each passing. And this is why we're able to then hit distinct beam pipes each time. You see it here. Here we have like roughly, how much do we have here? Like 18. He's counting them. We didn't do this tour for some time.
16.
16. Oh no, I think it's 18. Okay, whatever. So we have to hit these beam pipes all the time. And I mean, as already mentioned, if you have a fixed amount of energy or additional energy, then you're able really to go through these pipes.
Yes. Yeah, and this is our idea. This first stage you see here, which is called RTM1, was built in 1979. And at this time, this was actually vMAMI. And
actually, there was a linear accelerator before.
Yeah, but as vMAMI was built, this was the only thing. And then one made experiments and said, yeah, okay, now we made everything which is possible. We need more energy for further experiments.
Yeah, so after this accelerator, just to give you a number, we have 14 MeV.
Yeah, 14 MeV. And I bring once again back the map of the Institute of the Accelerator. I'm sorry to stop that video. So you can see the pre-accelerator. I make my picture very, very little here. The pre-accelerator is, here's the source. And you see here RTM1. This is that little thing in here we have just seen with the animation of the dipole magnets.
So this is more or less really a tabletop accelerator.
It's not very big.
Yeah.
And then one did one stage after the other in large vMAMI. Yeah. So then in the 80s,
I think like 4 years later, they built it.
RTM2 was built up. Then same thing again.
More or less the same, just a little bit bigger. And I think there we have like 51. I'm sorry, I'm in the midst of words for these recirculating returns.
Yeah.
Thanks a lot.
Yeah, and then so we can skip RTM2. It's exactly the same thing than RTM1. And then in the 90s, the RTM3 was built, which is the biggest stage. And the thing is, if we do a tour which is not virtual, most people are impressed by the things you see in there. And we said we have seen, okay, this is not working so good when you do this virtually because you just see a video. But we want you to enjoy those impressions, and therefore we made a little video which we will show you now without saying anything. Enjoy those pictures. So here we are back.
Okay, so there you saw the third stage, and most likely you recognize the different parts. So you saw the big green magnets, and you see this is not a tabletop accelerator anymore. These magnets have roughly 450 tons each, and think a field of 1.3 Tesla.
Yes, it's around that.
And there we have 90 return pipes. And after this, we hit, I think, 855 MeV.
Yes, okay, exactly.
Yeah.
855. And you see, this is very big. And if you need more energy now, you can think about, okay, the next stage would be even bigger, way bigger. And so one needs something different.
I mean, you're already, sorry to interrupt, you're already going off for the next stage. I mean, perhaps let's use this again to ask you for questions and to have a small look on the map here, because you see we have one experiment already, it's called X1, which just uses this stage. And actually this uses synchrotron radiation to study structures of crystals. So, but we're sorry, we're not going to show you this hall, but just that you know, we have at this stage already we're using this, we're providing electrons or in this case, synchrotron radiation of photons for this one experimental hole. And now again, the question, if you have any questions, or
This would be a good spot.
it's always a good spot,
Yeah.
but I mean, would be now that we're leaving the classic racetrack microtrons and go into the last accelerator stage. Which energy they have?
Yeah, but we don't have photons, we have electrons.
No, the photons for X1.
Ah,
Actually, I'm not so sure. Below 855 MeV. I don't know how much is kept really by the electrons. I would guess like half of it, but I may check this for you if it's really of interest, and we'll come back to you. We'll write this down.
are there any further questions on this point? Okay, I don't think so. Then we can go on to the HDSM. So this is here then. And yeah, HDSM stands for harmonic double-sided microtron. And in here we will change the idea of how that accelerator works slightly. You will see. So we're entering the hall now, and again you see there things you have seen before. There are magnets, dipole magnets. You see also cavities. In general, it looks a little bit way more complicated actually. And you see in here is one cavity. Again, we're using the same technology of cavities. The major difference of that idea of acceleration in comparison to vMAMI RTM 1, 2, and 3 is that we don't accelerate on one side of the circulation, but on both sides. So, and therefore we have to change things. First of all, we need more than 2 magnets. We need 4 magnets. And you see when I go to the next slide, this is the idea of acceleration. And so you see there are 1, 2, 3, 4 magnets, and between on both sides between you see the individual tracks, and therefore you can then accelerate here and here, which saves a lot of space. There are
this is the main argument. I want to ask you why did we do, or why did the physicists before us actually build it in such a way?
One accelerator physicist told me they first calculated to build that stage with the same technology as before, with the RTM technology, but this would be so big when you want to come to the same energy of 1.6 GeV in the end, because the radii they are of those tracks, they are getting bigger and bigger. So you need a really big structure or stronger magnets, of course, which was an issue in that time.
Sure.
I guess today one would just use some superconducting magnets, and this would be then more compact, but this was in that time not so easy.
But I mean, this is the main idea. Sure, before we always had this bending of 180 degrees and the 2 dipoles, and this is why here we're using 4 dipoles and just bending the tracks by 90 degrees.
And there's actually a question about that in here. See if there's a plan to replace that dipoles with superconductors, and I don't think so.
No,
because we are just building a new accelerator, and it's not easy to tell what will happen in general with vMAMI afterwards. So what the future will show that, but there isn't the plan to change that technology.
Or not that we know of it.
Not that we know.
Perhaps
we are PhD students. one doesn't tell us that.
Actually, there are no plans.
Yeah.
Yeah. Now we are more or less focusing on the new accelerator, which will have not a higher energy as one would suggest, but will have a lower energy but a higher beam current.
Way higher, an order of magnitude higher. So, yeah, and as I said, we are then at the maximum energy of 1.6 GeV. This is everything vMAMI can do. I wanted to tell you one thing. It's called HGSM, which means harmonic double-sided microtron. And you can see harmonic comes from the fact that we have here a frequency of 4.9 gigahertz and here a frequency of 2.45, which you know, this is the frequency we had before. And this has to be done because otherwise it would come to resonance catastrophe. But I'm not an accelerator scientist. I'm unfortunately don't understand why. Yeah. But yeah, this is therefore that technology is a bit more complicated to get the beam stability one aims for. One has to do some more complicated things.
We may try to do it afterwards on the blackboard.
Yeah.
Actually, I had it explained at one time as well, but I'm not so sure. So please don't ask about this.
No, we don't have the explanation here. Okay.
So let's see some experiments.
Yeah.
Actually, now you saw the last accelerating stage. So these, oh no, we have this one number here. This is the final energy of the vMAMI accelerator. And to accompany this, we didn't mention it, but we're able to reach a beam current of 100 microns.
Yeah, around that.
Around that. Yeah.
So the first experiment we have in there is the so-called A1 experiment, and we show you on the map. So briefly, we started in here. Here was the first two stages. Here you have seen the drone flight. This is RTM3, and then we went to this hall where HGSM is. And then we have the option to bring our beam either in A1 or A2. There were another experiment called A4, but here in that hall today, the new accelerator will be built. So they made a wall in here and separated those two halls, extended it with another new hall, and then MESA will be built in there. And so we first go to the A1 experiment.
Yep.
So
this is what you see when you enter the hall, and you see we have this huge spectrometers there. And just to guide you a little bit through this picture, I mean the beam is entering from the bottom of this picture, so below these two blue dipole magnets. Where it enters in a straight line. I mean, these dipole magnets below there are to bend the electron beam a little bit. But I mean, this is the main thing that we have there. Where you see me at this moment, there is the scattering chamber. So there we hit the target. And then we have this 3 magnetic spectrometers to detect and measure the scattered particles.
yeah, we have a chalkboard where this is explained a little bit better
in an easier manner.
So
yeah,
see the view from the top. Electrons come from down to up. In the middle here where paper is, we have a scattering chamber where we have our fixed target, and this can be anything. So this can be either a solid state target, which is maybe some metal film or some plastic film. But we also have the option to work with gaseous targets. So and we also have a liquid hydrogen target. Yeah, and then those electrons, they will be scattered and will be led into those three spectrometers. And what we want to measure in here is the momentum of these scattered electrons, because we want to know the Q squared, and we want to know the angle. And for the angular measurement, the first thing you do is, wait a second, gonna switch out the.
And just to mention this, perhaps we hopped too straight into this. To be sure about this, because we talked about X1 before, here at A1, we are really doing experiments with real electrons. I mean, this is more or less the, let's call it, simplest approach to use the electrons of the accelerator, just to have them shoot them straight at the target and measure the scattering particles.
Yeah, and if we want to measure the angle, you see there's a big black circle in here, and those spectrometers are movable on that circle. Yeah, and this is for itself very expressive, because they are really heavy. It's nearly
they have like 350 tons.
Yeah.
Each spectrometer, and they're, we call it, swimming on a thin layer of oil in this goniometer, and this is why you're able to place them, I think, with the resolution of 50 micrometers.
Yeah. But this is not enough. Therefore, the more precise angle will be measured inside of the spectrometer. So there's an angular acceptance of this spectrometer, and we measure both the momentum and the angle inside the spectrometer. And you can see in here.
Yeah, show this picture again. Let's explain. Most likely, most of you know this, but let's see how spectrometer works, or magnetic spectrometer. We see it here on the left. So it's a system that is capable of mapping particles with the same momenta, or with the same momentum in this case, on one plane in the focal, on one point in the focal plane. So like with the lens system, you are able to focus different particles, but with these magnets, you're able to, more or less with the transfer matrix, how you shape the magnets, the dipoles in there, you're able to choose which characteristics you wanna focus on, and how they are built. You're able to focus the momenta on one dimension in the focal plane, and as the name suggests, you also have this second dimension, and there we have a mapping of the scattering angle, actually of the in-plane scattering angle, and this is what you, I think, what you want to mention. So we are not just able to position the big spectrometers very accurately, but then inside this acceptance, we are also able to, or we're on top of this, able to measure the scattering angle even better. Like, you have a resolution for this?
So for the momentum, we have a relative resolution of 10 to the minus 4. And for the angle, I'm not so sure actually, but it's very very accurate.
I think 0.05 degrees,
something
more or
like
less, in this region.
So what we do have here, nothing. Okay. Finally.
So, but what we're measuring here, I mean, now we have these big spectrometers, so we are shooting at something with electrons, and what we learn from this.
Yeah. Okay. We can derive then the cross section and the form factors, and especially we are interested in for electromagnetic form factors of, for instance, very traditional measurement in here, the radius of the hydrogen the radius of the proton. And
I mean, this is what this hall is
famous for. This hall is famous for. Of course, we do a lot of other measurements. We did also the neutron radius and the deuteron radius, but also measurements on hypothetic dark matter particles like the dark photon. We did a lot of measurements concerning kaons.
So hypernuclei. Actually, there's a fourth spectrometer, smaller one, which is called chaos. A Kaon spectrometer, which is not seen in here, but
a little bit here in that corner. You can see. We have another video in here that shows a little bit the way of an electron going through A1. So we're coming out of the accelerator, going here through that beam pipe. You see in the middle, we see then here the scattering chamber. We will then be scattered and propagate through that spectrometer until we are detected in this area where we use multi-wire drift chambers and the top of the spectrometer we have an additional Cherenkov detector.
Yeah, and surely I didn't even mention this. I forgot to mention this. So we have these multi-wire proportional chambers as trackers to determine the position, and then we also we have several layers of them, vertical drift chambers actually. And we have also some scintillators for timing and Cherenkov detectors.
So now, since there are only a couple of minutes left,
what time do we have?
We have 5 minutes.
5 minutes left. Okay.
5 minutes left. Yeah. I would rather use this time to answer questions. Hopefully, there are a lot of questions. You can also use your microphone, switch on your audio and ask us the questions if you want.
And so while you think about questions, because we skipped this now, we're sorry, we have this second experimental hall. If you visit us here or visit the next virtual tour, perhaps where we have the time to show this, but just to complete it, that you know it, there we're using photons. So we hit a radiator with the electrons and then even are able to measure the remaining energy of the electron with the tagger. And then we have there a 4-pi detector, the so-called crystal ball.
Good old crystal ball.
To measure like polarizabilities and stuff like this. So this more or less completes the experimental course.
So now, feel free to ask multiple questions.
Multiple questions, yeah. And perhaps let's choose a nicer picture.
Power consumption. You mean, I guess, for the entire?
We have,
we have something.
Also have a small video for
backup
this.
Slide. Here. So, yeah, I'm sorry. This isn't German here. So this is the usual. Usually we have 7,000 hours of beam per year. Yeah. And you see, it depends on which stage you use. So if you don't need the HDSM, you have way less energy.
Yeah, so this is a different naming scheme. So MAMI B means racetrack 1 to racetrack 3.
Yeah.
So with 850 MeV.
Yeah. But this is roughly that. More questions?
I mean, there we have, I think, which are doing more or less similar physics, JLab.
But are there okay, let's read the question. So the question was, what are the main competitors of MAMI? I guess there are no Are there any competitors in physics? I mean, we are.
Yeah, okay.
Yeah.
Also a good way to answer this.
Yeah.
I mean, sure.
Yeah, if you want to.
Philosophical way
Yeah.
of answering this. If there are competitors or collaborators.
Yeah, I guess JLab. If you want a competitor, it might be JLab or.
Yeah, sure. A lot of the stuff we're doing here, they're also doing about that.
But I don't think that anyone sees them.
I mean, I like your answer.
Yeah.
Okay. Achim is also in there. Thanks.
Can I ask you about the future? So what are the future plans or programs or main experiments which are either running now or plan to be running?
I mean, from our point of view, now we are really, as Stefan told already, we are really focusing on this new accelerator that we're building. So perhaps now that I saw, sorry, that that Achim is in the room, perhaps we may forward this question even to you, if it's fine with you, Achim.
Yeah, I mean, one interesting new initiative is actually measuring with vMAMI cross-sections in electron scattering on nuclei, which serve as impact for the future program in neutrino physics. So, you know, in particle physics, the Dune experiment in the US and also Hyperkamiokande are large-scale future projects to measure the properties of neutrinos, CP violation, and so on. And in order to extract this information, one needs to have a detailed understanding of the neutrino nucleus cross-section, which is, of course, notoriously difficult. And therefore, at Jefferson Lab and also at vMAMI, a new program has been defined in order to measure the electron nucleon cross-section, inclusive measurements, semi-inclusive measurements, which serve as impact for the neutrino program. This is certainly a very interesting new program. Apart from that, there are also a couple of measurements in the field of few body physics, where we also have a local theory group here providing the information. And of course, we eventually will also continue our program of searches for particles beyond the standard model. Stefan mentioned, I joined late this meeting since I had to teach. He mentioned the searches for dark photons, which was extremely successful, this program. And in principle, many more things can be done also in the case of axion searches and so on. But as the two guys mentioned, we are constructing a new low energy accelerator, MESA, and that will, of course, this is actually being finalized now in the next 2-3 years. And this will, for the time being, of course, be a very important program for MINDS for the upcoming years.
Yeah, we mentioned this more than one time.
Yeah, yeah, I'm afraid that we did too much advertising.
But the idea is that vMAMI and MESA will run in parallel, and therefore this will certainly not be the end of vMAMI.
Yeah. Sure.
So, they are proposed to be run in parallel, you mean? Okay.
They can be running in parallel. Yeah.
Okay. And where is vMAMI? I've seen something, but I didn't really get the point. Where is physically going to be?
So vMAMI is underneath the Institute for Nuclear Physics, which is on the campus of the University of Mainz.
Okay. Thank you.
Again, was it your question?
What is your question?
Where it's physically situated? Or
yes, physically situated.
Yeah. Sorry, I think you were interrupted. Hear you clearly.
Okay.
I guess your microphone is muted.
Mine is not muted.
Ah,
Now we hear you.
Okay. No, you answer. I was wondering physically where it's physically going to be.
Didn't we have this picture also, the overlay of the floor plan and the Google Maps picture?
yeah.
Yeah.
So here you can see this is from Google Maps, and yeah, this is a part of the University of Mainz, and this is actually the Institute for Nuclear Physics. Here's the Helmholtz Institute. Here's our office. Here we're sitting currently. Here's Achim's office, and here's a new building, and then you can see here underneath in that area is vMAMI.
And perhaps you may show where we started.
Yeah, wait a second. And here will be Mesa later. And we started actually in here. Here's the lecture hall. I don't make it small. Here's the lecture hall, and we went here through that building, the floor. Then we have here we have been in our yard. We walked this way and entered here, and here then 8 meters. Under the
and actually, now that you see it, we promised to go into the counting, not into the into the control room once again.
We didn't.
Sorry.
Yeah, we didn't. Yeah,
we didn't.
Yeah. Any more questions?
Yeah, apparently.
Oh, I guess if there aren't any more questions, we are at the end of the tour.
Yeah.
And it was an honor for us to speak here. Yeah.
It was a pleasure for us to have you.
And if you have more questions afterwards, just write Stefan an email.
Or paper.
So it was a pleasure to have you here. Hopefully in a few years, we'll see you for the in person or for the tour of our new accelerator. And by this, have a nice day, nice afternoon. Come visit us here in person. And
so thank you very much. It was very nice. Bye.
Bye-bye.